In today's lecture, we are going to deal with a very small concept. Although the concept is small, but it is very important for the study of statistical mechanics. Actually, we will see the condition of equilibrium between two systems in thermal contact. In fact, in statistical mechanics, whenever you talk about the equilibrium between two systems in thermal contact, the condition is expressed in terms of a parameter which is called beta parameter. Actually, this beta parameter has a dimensions of a reciprocal of energy. Okay, and so you can also say that today we are going to see the concept of this beta parameter in terms of which we will express the condition for equilibrium of two systems in thermal contact. Okay, as you know, in thermodynamics, the equilibrium condition is expressed in terms of temperature, but here we will express the condition in terms of energy. And whenever you talk about statistical mechanics, we always think in terms of probability. So this condition will be also in terms of the probability of a system in equilibrium state. So to know what is this beta parameter and how we can express the condition for equilibrium between two systems in thermal contact, let us start with two systems. Let us say one of the system is A and another system is B. And we simply say that these two systems are in thermal contact. When you say that the system A and B are in thermal contact, what does it mean? Actually, in thermodynamics, whenever we talk about the thermal contact, that means the exchange of heat energy may take place between A and B. It means heat energy may flow from system B to A and it also may flow from A to B. Okay? So if there is an exchange of heat energy between the systems A and B, then we simply say that the systems A and B are in thermal contact. One thing you should note here, that whenever you talk about thermal contact, that does not mean that the two systems are in physical contact. The two systems may be in physical contact, they may touch one another or may not touch one another. Because when the two systems are not in physical touch, even then there may be an exchange of heat energy between the two. And the condition for thermal equilibrium is what? This is only the exchange of heat energy. So we simply say that if the two systems which are capable of exchanging heat energy between one another, then we simply say that the systems are in thermal contact. So I have mentioned it here. You can see that the two systems capable of exchanging heat energy are said to be in thermal contact. Okay. Now we consider that these two systems A and B, which are in thermal contact, they are also in equilibrium. Okay, so you can say that A and B are two systems in thermal contact and they are in equilibrium. Now we specify some of the important quantities associated with these systems A and B, in terms of which we will discuss the condition for equilibrium between these two systems. And for this, let us consider that E is the energy of the system A, we consider it, and E prime or E dashed is the energy of system B. Okay, and this ET represents the total energy of the system A plus B. Okay, as you know, if you are talking about only these two systems, then the system A, combination of system A plus B will be actually an isolated system. So this total energy ET will be definitely constant. Although E and E prime may change because there is an exchange of energy between A and B. So E and E prime may change, but ET will remain constant. Okay. Now we also consider that this WE, as you have studied in the previous lecture, the concept of macro state and micro state. Okay. And when you say that total number of micro states of a system, that is also called actually the thermodynamic probability. So we consider here that this W of E, this is the number of microstates or thermodynamic probability in the energy range between E and E plus delta E naught. Although this delta E naught is very small, so you can also say that when the system A has energy E, then the total number of microstates or the thermodynamic probability of this system A is given by W of E. It means this probability is actually a function of energy E. Okay. And in a similar manner, we also consider that this W prime of E prime represents the number of microstates or the thermodynamic probability in the energy range between E prime and E prime plus delta E naught for the system B. Okay. So these are the thermodynamic probability or the microstate number of microstates for system A and system B when their energy are actually E and E prime. Okay. As you know that the probability of A possessing a particular energy, let us say E, is actually directly proportional to the number of microstates or the thermodynamic probability. Actually, this fact we have also studied in the previous lecture. So if you say that the probability of A possessing energy E, which is represented by P of E, will be proportional to W of E. And when you will remove this sign of proportionality, you have to put a proportionality constant. So this P of E, which is the probability of system A possessing energy E, is given by C times W of E, where C is the proportionality constant. And in the similar manner, the probability that the system B will have an energy E prime will be what? That can be expressed like this equation 1 in this manner, that the probability of B possessing energy E dashed is given by how? This is P of E prime equal to C prime W prime of E prime. Actually here this C prime is also proportionality constant. Okay. Now definitely you have an idea of probability theory. Whenever you know the probability of two events and you are now talking about the composite event, you know, since the probability is a multiplicative property, so the probability of a composite event is found simply by multiplying the probabilities of the individual events. Okay. Since probability is a multiplicative property, remember, it is not an additive property. So if you want to find the total probability or the probability of a composite event, you have to take the product of probabilities of individual events. Never you can take the sum of probabilities. Okay. So the probability of the composite event, you can say that the system A and B will have energy E and E prime respectively simultaneously. It means if the system A has energy E, system B has energy E prime at the same time, then the probability for that event is given by P of E comma E prime. Okay. And that will be equal to the product of probability P of E and P of E dashed. Okay. This is actually the probability of the composite event. Okay. So you can say that this will be equal to what? We have seen in equation 1 and 2 that this P of E is equal to C times W of E, and P of E dash is equal to C prime W prime of E dash. Okay? And therefore you can say that this P of E comma E prime is equal to CC prime times W of E times W prime of E. Okay? Now to get the condition for equilibrium of these two systems A and B in thermal contact, we will have to some actually mathematical steps which must be followed to get the result. And for that, first of all, we take the natural logarithm of this equation 3. So when you will take the natural log of this equation 3, what will be the result? You can see, since in RHS there is a product of four quantities, these are C, C prime, W of E and W prime of E prime. And when you will take log, there will be the formula log A times B is equal to log A plus log B. And applying that formula, you can see that ln P of E comma E prime, E will be equal to what? This will be ln C plus ln C prime plus ln of WE and ln of W prime of E prime. Okay. Now, as you know that for equilibrium state, this probability should be maximum. Okay. Actually, the equilibrium state always corresponds to maximum probability. Okay. This is actually the idea of Boltzmann, that every equilibrium state corresponds to a maximum probability. Why? Because our system has always a tendency to reach to the equilibrium state, and so the probability of finding a system in equilibrium state is always maximum. Okay. So if you are talking about the equilibrium state of your system, definitely this probability P of E comma E prime must be maximum. And so its logarithmic value ln P of E comma E prime will be also maximum. And if it is maximum, you know that its derivative will be 0. So for the condition of maxima, you can say that the partial derivative of this ln P of E comma E prime with respect to E must be equal to 0. So I have written here, you can see that del ln P of E comma E prime del E is equal to 0. Okay. Now we will substitute the value of this ln P of E comma E prime from here, and we will differentiate this expression with respect to E. As you know, this ln C is a constant, so whenever you will differentiate it with respect to E, you will get 0. So derivative of ln C is 0. Similarly, ln C dashed is also 0. Ln C dashed is also constant, so its derivative will be again 0. So this is also 0. And this ln W of E, it is a function of E, so it will be differentiated, and this will be del E ln W of E, and plus the last term will be what? This is del E ln W prime of E prime, and that will be equal to 0. Okay. Now we will simplify the last term here, because here this last term, in last term the function is actually a function of E dashed, and we have differentiated it with respect to E. So we must see what will be its derivative with respect to E dashed. Okay. So this first term remains same. This is del E ln W of E, and plus. Now by the rule of function of a function, you differentiate this last term. So you can write this last term like this. This is del E prime ln W dashed of E dashed, and times del E prime by del E, and this is equal to 0. Okay. Now we will see what will be actually the value of this del E prime by del E? What will be the value of this factor? Actually, as I have told you earlier, that the total energy of this composite system A plus B is ET, and that will be actually equal to E plus E prime, where E is the energy of the system A and E prime is the energy of system B, and this is actually equal to constant because the energy exchange takes place between A and B. So the amount of energy which will be lost by A, same amount will be gained by B, or the energy lost by B will be equal to energy gained by A, and so the total energy remains constant. So taking this fact under account, you can easily find what will be the value of this del E prime by del E. Okay, so let us see. I have obtained the value, and this will be actually minus 1. You can see, since ET you know is equal to E plus E prime, and that is equal to constant. Since E plus E prime is constant, so its derivative with respect to E will be 0. So let us differentiate this E plus E prime with respect to E. So I have operated the operator del E on it, and this will be equal to 0 because the derivative of constant is 0. Okay. Now del E operator will be operated on both E and E prime. You know del E by del E, that will be equal to 1, and the second term will be del E prime by del E, and that is equal to 0. So you can see that this del E prime by del E is equal to minus 1. So in this way, you have obtained the value of del E prime by del E. Now let us substitute this value of del E prime by del E in this equation number, I have not, this equation number 4. So instead of del E prime by del E here, we will substitute minus 1. So what will be your result? You can easily see. Our result will be del E ln W of E minus del by del E prime ln W prime of E prime equal to 0. And so that you can write del E ln W of E equal to del E prime ln W prime of E prime. Actually, this is the condition for equilibrium of two systems in thermal contact. You can see according to this equation 5 that the function, this function del E ln W, that is the function del E ln W must be equal for both of the systems. So you can say in terms of statistical mechanics, if the function del E ln W, where you know W is the thermodynamic probability or the number of microstates, if this function is same for the two systems in thermal contact, then those two systems will be in equilibrium. So this equation 5 represents the statistical condition for equilibrium of two systems in thermal contact. Okay. Actually, this function is represented by the symbol beta, and so this is also known as beta parameter. Okay. Actually, all those facts I have mentioned it here. You can see this will be just okay. Which the facts which I have just described, I have already mentioned here for your convenience, so that you can write down these things in your notebook, because when you not write the language, after some time people gets does not memorize those things, and so that is a problem for those. So you can see I have mentioned it here that this is the required condition for equilibrium between two systems in thermal contact, and thus statistically the two systems in thermal contact will be in equilibrium if their functions del E ln W are equal. Okay. Now, as I have told you that this function del del E ln W is generally represented by the symbol beta, and this is called beta parameter. Okay, and so you can see that the beta parameters for our system A and B under consideration are what? You can easily see. This beta of E, this is the beta parameter for the system A, because you have considered that E is the energy of system A. And so this beta E is equal to del ln W by del E. Okay. Now, ln W is directly a function of W, and that W is a function of E. So this is just a function of function, and so you can write this like this. This is del ln W by del W times del W by del E. But you know this del ln W by del W, this is equal to 1 by W, and so this is 1 over W del W by del E. Okay, and similarly the beta parameter for the system B which has energy E prime, that is given like this. This is del ln W dashed by del E dashed. Okay, and this can be written as del ln W dashed by del W times del W by del E prime. Again, this del ln W prime by del W is equal to 1 over W prime, and this is del W prime by del E. So these are the beta parameters for the systems A and B possessing energy E and E prime. Okay. And as I have told you earlier, you can see from this the expression for beta E and beta E prime that this is equal to 1 over W del W by del E. Or you can see this expression del ln W del E. Since logarithmic value of W will be a number, so you can see that this del ln W will have no dimension, this is a number, and this del E is actually will have the dimension of energy. So you can easily say that this beta parameter has a dimension of reciprocal of energy. It means its dimension will be joule inverse, because joule is the dimension or unit of energy. So its its dimension will be joule inverse, or its unit will be joule inverse. Okay, and as you have seen that for in equilibrium condition for two bodies in thermal contact, these beta parameters must be equal, because you have obtained the earlier that for equilibrium this del E ln W of E is equal to del E prime ln W prime of E prime, and you have actually considered this as beta and this as beta prime. So you can say that if this beta parameter for the two systems in thermal contact are equal, then statistically we say that the systems are in equilibrium. Okay, so beta is equal to beta prime. This is actually the condition for equilibrium of a system in thermal contact. Okay, as I have told you earlier that in thermodynamics we talk about the equilibrium in terms of temperature. So if T is the temperature of system A and T prime is the temperature of system B, and both are in thermal contact and in equilibrium, then in equilibrium actually there will be no exchange of heat, and in that condition we simply say that this T should be equal to T prime. Only then the systems will be in thermal equilibrium. Okay, this is in accordance with the 0th law of thermodynamics. Okay, now this so you can say that according to statistical mechanics, equality of temperature means equality of beta parameters. When you say that T is equal to T prime, in statistical mechanics we simply say that beta is equal to beta prime. In fact, as you have seen that this beta has a a unit of which is reciprocal of energy. So, and this, if this quantity kT has a unit of energy, then this kT may be written as 1 by beta. Okay, and this kT prime will be written as 1 by beta prime. Actually, here this k is a constant, and this constant must have a unit joule times Kelvin inverse, because when you will write kT, then and the unit of k is joule Kelvin inverse, and T has a unit of Kelvin, then it will be equal to joule. And as you have seen that this beta should have a dimension of joule inverse. So we can say that if the quantity K has a dimension or unit of joule Kelvin inverse, then kT can be represented by 1 by beta. Okay. Actually, this constant K is a universal constant, and this is known as Boltzmann constant. In fact, after this lecture, we will study the entropy and probability. That is the Boltzmann theorem connecting the entropy and probability. We will learn in the forthcoming lecture. And there, I will explain that this constant K is nothing. This is simply the Boltzmann constant. I have not explained how you can say that this K is Boltzmann constant, but in the forthcoming lecture you will see I will explain in very detail that this constant is nothing. This is simply R divided by Na, where R is universal gas constant and Na is Avogadro number, and this R upon Na is K, which is called Boltzmann constant. But how it is Boltzmann constant we will learn in the forthcoming lecture. So I hope you have understand the condition for equilibrium of two systems in thermal contact in terms of beta parameter. It is although a small condition, but it is very important for you, and sometimes in your university examination directly question is asked like this, that discuss the condition of equilibrium in terms of beta parameters. Okay, but the concept is simple. If the beta parameters of two systems are equal, then in statistical mechanics we simply say that the systems are in thermal equilibrium. Okay, so I hope you have learned all these things. This was a very simple concept, and as I have told you, in the forthcoming lecture we will learn about the Boltzmann theorem, which is called Boltzmann entropy theorem, which connects the entropy and probability in the forthcoming lecture. And that result, which is actually S equal to K log W, is a very important result, and it finds its application at several places in the study of statistical mechanics. So this Boltzmann theorem connecting the entropy and probability of a system is very important. And we also say that actually this Boltzmann theorem connecting the entropy and probability is nothing. This is simply the statistical definition of entropy, because thermodynamics, does not give the real picture of entropy. In the concept of entropy in thermodynamics is incomplete, and so what is actually entropy of a system, that was explained by Boltzmann in his theorem connecting the entropy and probability. And all these things we will learn in the forthcoming lecture. Okay, thank you very much.